Hello, Professor. My name is Kumudini, and today I'm going to demonstrate my walkthrough for assignment 3, which is the Embedded Debug Logging System assignment. The business case here is something every real product deals with. When software fails at a customer site, you often don't have a way to reproduce the problem in the lab, and built in logging is what lets engineers understand what went wrong without needing physical access to the machine. This assignment asked us to build that as a client server system using UDP sockets where any process can embed a lightweight logger, filter what it reports by severity, and send that data to a central server. And the server can even change the filter level remotely while the process keeps running. So now let me walk through the code before I demonstrate it. Firstly, let me walk through the code before I demo it. So, I have two directories inside my assignment 3 directory. One is server and the other one is process. So, let's look at what we got in our process directory. So, let me start off with logger.h, which is the logger header file. So in my logger header file, I have so in my logger header file, this defines the public interface every process uses. An enum for the 4 severity levels, debug, warning, error, and critical, and 4 functions: initialize log, set log level, log, and exit log. Now, logger.cpp is where the real work happens. So let me go to logger.cpp. So as you can see, initialize log creates a initialize log. Okay, yeah. So initialize log creates a UDP socket, sets its non-blocking with FCNTL here, yeah, configures the server's address and starts a background thread using pthread create. Here, like this. And the background thread's whole job is to listen for commands coming back from the server, specifically a set log level message, so the filter can change without restarting the process. Because the socket is non-blocking, if there's nothing to read, receive from immediately returns immediately instead of hanging slow. So I sleep for 1 second and before checking again rather than burning CPU in a busy loop. The log function is the core of this assignment. It first checks the message's severity against the current filter level, and if the message is below that threshold, it's dropped immediately before any formatting or network work happens. So filtering out debug spam is genuinely cheap. If the message passes the filter, I build a timestamp with ctime, format the message with the severity name, file name, function name, line number, and the message text, and send it to the server with send to. Every access to shared data, the filter level, and the socket is wrapped in a pthread mutex, since the main thread and the background receive thread both touch the data concurrently. The exit log flips a flag to stop the receive thread's loop, joins that thread so we know it's actually finished before continuing, then closes the socket and destroys the mutex. That ordering matters because closing the socket before the thread stops using it would be a race condition. Now on the server side, let's look at what we got. These are the files I have. So let's look at what we have in the log server.cpp file. So in my log server.cpp, it follows a similar pattern. It brings a non-blocking UDP socket, spins up in its own background thread that receives incoming log messages, and then tries to write them to server.log. And the main thread runs runs an operator menu. Um, yeah. So the main thread runs a menu with three options. Set the log level, um, and which sends that set log level command back to whichever process most recently sent a log, dump the log file to the screen, and shut down. Just like the logger side, every access to the shared log file descriptor and the last known client address is mutex protected. Now let me show it running. So I will start the server first. It prints. Okay, so let me say make. And now I run the log server. So it says that it's listening on UDP port 6000 and shows the operator menu. In the second terminal, I'll start the process. So I make it, and uh, using the provided travel simulator, I will which drives 4 cars and logs fuel events continuously. So back on the server side, I'll choose option 2 to dump the log file. So let me say dump the log file. And you can see debug, warning, error, messages coming through since the filter starts at debug by default. So everything passes. And then we press any key to continue. Now I will choose option 1 and raise the filter to warning. So which is, let's say, 1, right? So I'll press enter. So let's wait for some time and dump the log again. Okay, so now let me dump the log file here. So here we can see something very interesting, which is notice that the old debug entries, at this timestamp, we've run it around this time, right? So we notice that there are no the old debug entries from before the change are still there. Before the change, you can still see that those debugs are there. But since dumping shows the entire file, not just what's new. But looking at the timestamps after the moment I made the change, there are no debug lines at all, only warning and error. I can push this further and set the filter to critical, and since this program never actually generates a critical severity event, waiting even 30 seconds produces no new log entries whatsoever. So let's do that. Now I set the log level to 3 and I wait for some time and I dump the log file here again. So yeah, so it's showing the things at 137, but there are no new basically it cannot generate any critical severity event. Waiting even 30 seconds produces no new log entries whatsoever. because the filter suppresses everything, not just the lowest tier. Alright, so finally I will show shutdown on both sides. So pressing Ctrl C on the travel simulator triggers its signal handler, which lets the current loop finish, prints each car's final fuel report, and then calls exit log to cleanly shut down the logger thread. So we go to the travel simulator side and I press Ctrl C. So we can see that there is a final fuel report, and then it calls the exit log on this end and to cleanly shut down the thread. So, and this can choose you to shut down the server, joins its receive thread, and closes cleanly as well. So here I got my menu to be shut down, 0, so I choose it and it's shut down. One real challenge I ran into wasn't actually a bug, it was a misunderstanding on my part while testing. So after changing the filter level, I dumped the log file and still saw debug lines, and my first reaction was to assume the filter had failed. What I hadn't accounted for was that the dump options reads and prints the entire log file from the beginning every time. It's not a rolling view of only new activity. So those debug lines were just old entries written before I made the change, still sitting in this file exactly like they should be. So once I looked specifically at the timestamps after the moment I sent the level change, I could clearly see that no new debug entries appeared. It was a good reminder that when you're testing a system like this, you can't just eyeball the output. You have to think carefully about what the test is actually proving and match your evidence. In this case, it's the timestamps to the specific claim you're trying to verify. So, overall, I think this assignment met the core requirements solidly. The logger correctly filters by severity before sending anything over the network. The background threads on both sides and handles receiving concurrently with the main thread without race conditions thanks to mutex protection. The filter level can be changed dynamically without restarting the process, which was the trickiest and most interesting part of the whole assignment. So thank you so much for watching my video. This is the end.